Welcome everyone in this lecture of statistical mechanics. In this particular lecture, I will discuss about the helium 1 to helium 2 transition, or which is commonly known as lambda transition. Now let me discuss about the facts about the helium. So in this slide, I will discuss about some of the special properties of helium 4. The weakness of the interatomic interaction makes helium a universal weighting agent. So, interatomic interaction is very less in helium. Second point is that as the helium atoms have a stronger attraction for practically all other molecules, they easily spread over the surface of any substance. Next is that due to its light mass, the helium atom undergoes large 0-point fluctuations at T is equal to 0. This particular point is very important. I am again repeating, that is, the mass of the helium atom is very low. That is why the helium atom undergoes 0-point fluctuations at T is equal to 0. These fluctuations are sufficient to melt from a solid phase, and thus helium remains in a liquid state at ordinary pressure. So, helium remains in a liquid state at ordinary pressure. We have to keep in mind about this fact. Next is that pressure of over 25 atmospheres are required to sufficiently localize the helium atoms to result a solid phase at T is equal to 0. So, you need some pressure of about 25 atmospheres to localize the helium atoms. I have previously told that it is a natural tendency of the helium to remain in a liquid state, but still if you want to solidify it, you need a pressure of about 25 atmospheres. A remarkable property of the quantum liquid at 0 temperature is that unlike its classical counterpart, it has 0 entropy. So, this is a property of the quantum liquid at 0 temperature, that it has 0 entropy. Now, some other facts about the helium. So, now I will discuss, that is what is known as evaporative cooling of helium. So, for this you need a chamber. You see that here there is helium, liquid helium, and helium can be cooled down by a process of evaporation. Suppose you want to cool down the helium, then by the process of evaporation you can cool it. So, for that purpose what you have to do, liquid helium is placed in an isolated container. So, this is a particular container and you have placed liquid helium in this container which is in equilibrium with the gas phase at a finite vapor density. So, this particular liquid helium is in equilibrium with the gas phase. As the helium gas is pumped out, so you see that there is a particular pipeline through which you can pump out the helium gas. So, through this pipeline you are pumping out the helium gas. So, what will happen, that is as the helium gas is pumped out, part of the liquid evaporates to take its place. So that means if you pump out the helium gas, then you will observe the evaporation process. The evaporation process is accompanied by the release of latent heat which cools the liquid. So, the liquid is cooled by the process, that is by the process of evaporation. So, evaporation process is responsible for cooling of the liquid. The boiling liquid is quite active and turbulent, just as a boiling pot of water. So you will observe that is it is like a boiling water. So such type of observation uh, you can there can happen. So however, when the liquid is cooled down to below 2.2 Kelvin, this particular fact is very important. So by the process of evaporation, the liquid helium is being cooled, but there is a particular temperature, that is 2.2 Kelvin, below which when the liquid is step by step cooled and a temperature is reached whose value is 2.2 Kelvin, then what happens, it suddenly becomes quiescent and the turbulence disappears. So this particular temperature is very important, because below this temperature what happens, the liquid helium suddenly becomes quiescent and the turbulence disappears. So during the boiling you can observe the turbulence that I just explained in the previous point, that is you can observe the boiling liquid quite active and turbulent, but below the temperature of 2.2 Kelvin what happens, that is this turbulence disappears. The liquid on the two sides of this phase transition are usually referred to as helium 1 and helium 2. That means that is above the temperature 2.2 Kelvin, we will call the helium as helium 1, and below the temperature of 2.2 Kelvin, the helium will be referred as helium 2. Now, the property of helium 2 is a little bit unusual. So, that now I will discuss. So, the name of the phenomena is superfluidity. So, helium 2 has unusual hydrodynamic properties. It flows through the finest capillaries without any resistance. So, just look at the sentence, that is without any resistance. It can flow through the finest capillaries without any resistance. So, this is one of the important fact. The next point is that consider an experiment that pushes helium 2 from one container to another through a small tube packed with powder. So, there are two containers. You see that this is a container and this is another container. These two containers are connected through a small tube. So, this is the small tube which is packed with powder. You see there is some powder in this small tube. So, there are two containers which are connected by a tube, and that tube is packed with some powder. For ordinary fluids, a finite pressure difference between the containers, which is proportional to viscosity, is necessary to maintain the flow. Now, it is quite obvious. Suppose that the fluid is ordinary and you want to make the fluid flow from one container to the another container through this pipe. Now, there must be some pressure difference, because without the pressure difference the fluid can't flow. There must be some pressure difference, and this pressure difference should be proportional to the viscosity for the maintenance of the flow. But the point is that helium 2 flows even in the limit of zero pressure difference and acts as if it has zero viscosity. For this reason, it is referred to as a superfluid. So, this is the one of the remarkable property of helium 2, that is the zero pressure difference and zero viscosity. So, these are the unusual properties of helium 2. Now, another unusual behavior is there for helium 2, that is the absence of boiling activity. We have listened in the lecture regarding the Bose-Einstein condensation, that is the expression for pressure in Bose condensate is only a function of temperature and not the density. So this is one of the important feature of the expression for pressure for the Bose condensate. You see, for the Bose condensate, this is the expression for the pressure, and this expression shows that pressure is the function of temperature only. And you see in the right side there is no that is no function of the density. So pressure is a function of temperature alone, and pressure is independent of the density. So this is one of the important characteristic of the pressure for the Bose condensate. As such, variations in pressure are accompanied by change in temperature. So variation in pressure should be accompanied by the change in temperature, which is quite obvious from the above mathematical relation between the pressure and temperature. This is the reason for the absence of boiling activity in helium 2. So such type of pressure difference is such type of dependence of the pressure on the temperature is responsible for the absence of boiling activity in helium 2. Bubbles nucleate and grow in a boiling liquid at local hotspots. So when you boil some liquid, so we know that some bubbles nucleate there and grow there, and bubbles grow in some local hotspots. In an ordinary fluid, suppose if the fluid is ordinary, the variations in temperature relax to equilibrium only through the slow process of heat diffusion. So this particular process, that is the process of heat diffusion, is shown in the case of ordinary fluid, and through the process of heat diffusion, the variations in temperature relax to the equilibrium state. By contrast, if the local pressure is a function of temperature only, but suppose the local pressure is a function of temperature only, I have already shown you the equation, that is here pressure depends on the temperature only. So if the local pressure is a function of temperature only, there will be increased pressure at a hotspot. It must be the case, because if there is high temperature, so there will be high pressure, so there will be increased pressure at a hotspot. The fluid flows in response to pressure gradients. So the fluid flows in response to the pressure gradients. So if there is some pressure gradient, the fluid must flow and removes them, and removes the pressure gradient very rapidly. Very rapidly means how much rapidly? At the speed of sound in the medium. So this is the different activities for helium 2. So the main the theme of this particular slide is that liquid helium does not show any boiling activity. Next is the lambda transition. I have already told you, that is there is some transition at a point 2.2 Kelvin, because above the 2.2 Kelvin we are saying the liquid helium as helium 1, and below the 2.2 Kelvin we are saying the helium as helium 2. Historically, the experimental measurements of the specific heat of liquid helium, which led to the discovery of the so-called helium 1 to helium 2 transition, were first made by Kissom in 1927 and 1928. Struck by the shape of the CV versus T curve, which looks like lambda, Kissom gave this transition the name lambda transition. So you see the figure on the right side. So this figure, this figure is the behavior of the specific heat in case of liquid helium, where the x-axis shows the temperature and y-axis is the specific heat, and this particular figure is the variation of the specific heat with respect to temperature for liquid helium. So this particular curve looks like a lambda, mathematical symbol lambda, and this is the particular point that is below and above which the behavior of the helium changes. So if we call this particular region as a helium 1, then this particular region will be helium 2. So this is the particular temperature which separates the helium into particular regions, and the shape of this particular curve is like the mathematical symbol lambda. That is why this particular phase transition of the helium is known as the lambda transition. As a result, the term lambda transition temperature or transition point also came to be known as lambda temperature or lambda point. So the temperature of 2.2 Kelvin is sometimes also known as the lambda temperature or lambda point. It may be noted that there is a similarity of theoretical specific heat curve of ideal Bose gas with the experimental one for the liquid helium. Now you see the figure in the left hand side, this particular figure is the variation of the specific heat for ideal Bose gas. Now if you compare the figure in the right hand side and the left hand side, there is some similarity between these curves. This similarity prompted F. London to suggest in 1938 that the curious phase transition that occurs in liquid helium at a temperature of about 2.19 Kelvin might be a manifestation of the Bose-Einstein condensation taking place in the liquid. Indeed, if we substitute in the expression of Tc, that is the characteristic temperature or the critical temperature, the data for liquid helium, namely mass is equal to 6.65 into 10 to the power minus 24 gram and volume of 27.6 centimeter cube per mole, then we obtain a Tc, a value of 3.13 Kelvin, which is not drastically different from the observed transition temperature of the liquid. The interpretation of the phase transition in liquid helium-4 as Bose-Einstein condensation provides a theoretical basis for the two-fluid model of this liquid, which was empirically put forward by Tizza to explain the physical behavior of the liquid below the transition temperature. According to London, the N0 particles that occupy a single and entropy less state epsilon is equal to 0 could be identified with the superfluid component of the liquid, as we have learned in the Bose-Einstein condensation lecture. That is, some particles will be in the ground state. These particles are N0 number of particles, and some particles will be in the excited state, and such number of the particles is Ne. So the condensation to the ground state will occur below the critical temperature. Condensation will just starts at the critical temperature Tc, and the condensation will be continued up to capital T is equal to 0 Kelvin. So some particles will be in the ground state and some particles will be the excited state. So the number of particles which are in the ground state, they may be regarded as the superfluid component of the liquid, and the particles in the excited states any that particles will contribute for the normal component of the liquid. As required in the model of Tizza, the superfluid fraction makes its appearance at the transition temperature Tc. So this particular superfluid fraction will be appeared in the transition temperature Tc and builds up at the cost of the normal fraction until at T equal to 0, when the whole fluid becomes the superfluid. So the whole fluid becomes the superfluid at T is equal to 0, but the superfluid component makes its appearance at the transition temperature Tc. The actual temperature dependence of these fractions, that is the fractions of N0 and Ne and other physical quantities pertaining to liquid helium, is considerably different from what is expected from the theory of the ideal Bose gas. So this thing we have to keep in mind, that is the behavior of the different thermodynamical properties of liquid helium and that of the ideal Bose gas is exactly not same. London had expected that the inclusion of intermolecular interactions would improve the quantitative agreement. Although this expectation has been partially vindicated, there have been other advances in the field that provide alternative ways of looking at the helium problem. So, there is some more theory behind the behavior of the liquid helium. The behavior of the liquid helium and the ideal Bose gas is not exactly same. So, this is what about the behavior of the liquid helium, and I think you have understood those points, and for further understanding I request you to go through the textbook of Pathria and Bill and some other books like Mehran Kadar, and the content of this particular lecture has been taken from the book of Pathria and Bill, and I thank you all who have listened this lecture.